Okay, so one of the essential skills in this unit is predicting chemical reactions, which means we can give you a list of chemicals and say, if we just put all this stuff in a bowl and gave it a stir, would anything happen? If so, what? And we answer those questions using this table, which you should have in your data book, which here is entitled the Table of Selected Standard Electrode Potentials. And it's a list of chemicals that are good at oxidizing on one side and chemicals that are good at reducing on the other. And it's a ranked list. It goes from, in the top left corner, the strongest oxidizers. So up here in the top left, fluorine gas is the strongest oxidizer on this whole list, and indeed it is one of the strongest oxidizers known. And then as you go down this list, you get weaker and weaker oxidizers, fairly bad oxidizers, and at the bottom are the very weakest oxidizers. And over here, lithium ions are pretty much the weakest oxidizer you can imagine. Then on the other side, we have reducing agents going the other way. So lithium metal here in the bottom right is the strongest reducing agent. It's very good at reducing other things. And then reducers get weaker as you read your way up the table. Weaker, 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 until finally we get to the weakest reducing agent, which is fluoride ions. So fluorine is very good at oxidizing. It's an oxidizer and it's super good at it. Fluoride ions are a reducer, but they're really bad at it. Down here at the other end, lithium ions are a very bad oxidizing agent, but lithium metal is a very good reducing agent. Generally, being good at oxidizing makes you bad at reducing, and vice versa. So, when we use this list, they're going to give us some chemicals, and we're going to try to figure out which of them is the strongest oxidizer, which one is the strongest reducer, and those chemicals are going to react while everyone else just sits there and watches. So in this first example, let's say we have nickel metal. It's nickel with no charge. You can put a solid on it if you like to remind you of that. Silver ions. Silver only has one normal oxidation state, and that's +1. That would be aqueous. Now, if these are in solution, in theory a solution can be benzene or alcohol or some organic solvent or any number of weird things, but they're almost very, very often they're water, and so we're going to assume our solutions are aqueous, as in water solutions, unless we're told differently. So there's our list of chemicals: nickel, silver, water. So now we go to our table, and we're going to scan this table and see if we can find our strongest oxidizer and strongest reducer. The way you do that is you read down the left side and then up the right side. You read down the left side to find your strongest oxidizer, and that means we're looking for, just reminding you one more time, nickel, silver ions, or water. So over here, first row is fluorine. There's no nickel, silver, or water in that. Lead and sulfate, nope. Acid permanganate, nope. Gold, nope. Acid perchlorate, nope. Chlorine, nope. HNO2, nope. Acid dichromate, nope. Hydrogen, acid in oxygen, nope. Bromide, mercury, hypochlorite, nitric acid. Here we go. Silver ions, right there, are our strongest oxidizer. Let's make a note here, SOA. As soon as you find that one, you stop. None of the other oxidizers matter. So you read down the left side to find your strongest oxidizer. Next, you read up the right side, again looking for either silver ions, nickel metal, or water. Lithium, nope, nope, nope. This is lithium, potassium, calcium, barium, sodium, magnesium, aluminum, hydrogen, zinc, iron, chromium, cadmium, lead, cobalt. Ding. Here's nickel. Nickel metal is right there. That is our strongest reducing agent. Nickel is our SRA. Water, it turns out, is neither, so the water is not going to be participating in this reaction. It'll just be these two. So those are our two reactants. And the system we use for determining if the reaction will actually go, there's one we'll show you later that uses the voltages, which I actually quite like, but we'll keep it simple for now. The rule is draw a line from your strongest oxidizer to your strongest reducer, like so. If that line goes downhill, in other words, if the oxidizer is higher than the reducer, then your reaction will be spontaneous. It will go by itself. If you ever draw a line that goes like this, uphill, that represents a reaction that will not go by itself. It's non-spontaneous, meaning if you mix those chemicals, nothing will happen. So in this case, our line goes downhill. That means this reaction will go by itself. This reaction will occur. It's like rolling a rock down this hill. A rock would roll down this slope all by itself, but a rock won't roll uphill by itself. For that, you'd need some extra work. We'll get into how to make that happen later. So the reaction between silver ions and nickel metal will occur on its own. There will be evidence of a reaction. So this would be a yes. They don't ask what the evidence of a reaction is, and this one would have some, let's see, you'd have a color change and you'd have a formation of a precipitate, but we'll get into that later. For now, we're just interested in, is it spontaneous or not? Okay, let's see if we can get through the rest of these a little faster. Zinc metal, aluminum ions, and water again, because they said solution. So zinc, aluminum ions, water. So technically every time you do this, you start at the top and you go nope, 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 nope. But to make this go a bit faster, I will tell you that zinc is over here. And aluminum ions are here. You know what? Actually, that's a little sloppy. Let me do this right. If you read down the left side, you're looking for zinc, aluminum ions, or water. Zinc, aluminum ions, water. Here you'll find water, but it's only with hypochlorite, so that doesn't do us any good. Here's water with oxygen. That's no good either. They didn't mention oxygen in this case. Zinc, aluminum ions, water, zinc, aluminum ions, water. And I was going to say that aluminum ions were the strongest oxidizer, but that's not true. Water is right here. In this case, the water actually is more active than the aluminum is. That is our strongest oxidizer. And then going in the other direction, you find this is aluminum metal. That's no good. We have aluminum ions, so keep looking. And here we find our zinc metal. So there's our two reactants, the water and the zinc. And if you connect a line from those, it goes uphill, which means that reaction will actually not occur. So if you put zinc metal in a solution of aluminum ions, nothing will appear to happen. Okay, let's see. C is an aqueous mixture of copper-2 ions and iodine ions. That should be iodide ions, but oh well. And because it's an aqueous mixture, there's water also. So copper, iodide, and water. Clean up what we did last time. And it's copper ions, iodides, and water. So looking down here, copper, iodine, water, copper, iodine, water, copper, iodine, water, copper, iodine, water, copper, iodine, water. Do you see it yet? Here's iodine, the solid form, but we don't have that, so keep looking. Copper. Our reaction didn't say anything about pure iodine, just iodide ions, so we can't use this, but we can use copper too. So that is our strongest oxidizer. SOA. Now we go up the other side. Copper, iodine, water, copper, iodine, water, copper, iodine, water, copper, iodine, water. Come on, where are you? Cobalt, nope. Here's iodide, but only with silver, so we can't use that. Copper, iodide, water, copper metal, that's not it. Iodide. you connect those two with a line, it's uphill, meaning again, no spontaneous reaction. If you put copper ions and iodine ions together, nothing much will happen. Chlorine bubbled into bromide ions. That's Br minus. And it's a solution, so water also. So chlorine, bromide, water. Chlorine. Oh, that didn't take long. Let's get rid of what we did last time. Here's chlorine. Now we start going up the other side. Chlorine, bromide, water. Chlorine, bromide, water. Hello. Chlorine, bromide, water. Chlorine, bromide. Here we are. Bromide ions are a pretty weak reducing agent, but they are the best we have. If we hadn't caught bromide there, here's water. That would have saved us if we hadn't been able to find any other reducer. So, connect those with a line. That looks like downhill to me, meaning yes, this reaction is spontaneous. You will see evidence of a reaction. Aqueous mixture of copper 2 ions and tin ions. Okay, copper 2 and tin 2. Oh, and the ubiquitous water. Copper, tin, and water. Let's get this out of here. Copper ions, I have a feeling, are going to be the first one. There's copper. I believe that's our strongest oxidizing agent. Water's way down here, and tin is there. And going the other direction, here's tin metal, but we don't have that. We have tin 2 ions. Here we are. Tin 2 is our strongest reducer. Is that spontaneous? Yep, it's downhill. Next one's copper metal and nitric acid. Copper. Now, nitric acid is HNO3 aqueous, but when you put it in water, you may know already, if not, trust me on this, it dissociates right away. HNO3s break very easily when they fall in water, and they break into ions. So instead of HNO3, you're going to get H pluses and NO3 minuses. And also there will be water. So any of what we call the top 6 acids, more about them later, break up immediately and release hydrogen when you put them in water. And so these are the things that we're looking for. Copper metal and nitric acid. Get the previous question out of there. Fluoride, lead oxide, manganate, dichlorate, chlorine, HNO2, close, acid dichromate, oxygen, This, right here. This one is not obvious because it uses 2 pieces, but it is a perfect fit for what we have. 2NO3 plus 4H. These are exactly the pieces that nitric acid produces. So this essentially is the line for nitric acid. That is our strongest oxidizer. These 2 things working as a team are our strongest oxidizer. And if you go in the other direction, I pretty well guarantee it's going to be copper metal, but let's make sure. Hydrogen, H2O2, oh, copper right there. Copper is our strongest reducer. Will those react spontaneously? Yes, they do. What does that tell you? If you need to store some nitric acid, don't put it in a copper container. They'll react. The acid will eat holes in the container as it dissolves the copper into ions. So will those react? Yes. While we're at it, what could you store nitric acid in? Well, nitric acid is downhill to any of these, so you better not store nitric acid in copper or silver or lead or tin or cobalt or iron or any of those things. What could you store nitric acid in? Well, mercury is a liquid, so you can't make a container out of that. Are there any solids up here? Water, ions, lousy. Oh, gold. Sure, if you need to store nitric acid, just make your container out of solid gold and you'll be fine. Um, there are plastics that can stand up to nitric acid, and we normally use those or glass instead. But if you had to pick something off this list that could hold nitric acid, pretty much your only hope would be gold, because it's the only solid that's non-spontaneous to nitric acid. Okay, that was an aside, but we'll hear more about it later. Let's finish off these last two. Silver metal, Ag, in an acidified solution. Acidified means it's full of hydrogen ions. All acids release hydrogen or produce hydrogen somehow. So H plus of permanganate ions, which and they said solutions, so we get water also. So silver metal, acid, permanganate, and water. And you get a hit right away on this one. This is acid permanganate. Here's the permanganate, here's the H plus. It doesn't matter that there's an 8 in front of there. That just means you're going to go through 8 hydrogens for every one permanganate, meaning you'll use up your acid rather quickly. But just the fact that we have these chemicals means this is our strongest oxidizer. And what was it, silver metal? Yeah. If we look up the other side, no, 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 nothing there, nothing there. Silver metal will be our strongest reducer. Will those react spontaneously? Yep. Because the line goes downhill. That is a yes. And finally, will copper ions do anything in water? Cu2 plus H2O. Clear out the stuff from last time. Copper 2 ions are right here. They would be our strongest oxidizer. And do we have water someplace? Nope, 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 nope. Here's water with sulfurous acid. That's not the same thing. That's hydrogen peroxide. Da, 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 da. Here's water. There we go. So, will copper ions react with water? The uphill line says no, that reaction won't happen spontaneously.